Hi everyone, in this video I'm going to talk about Ekman Motion. Ekman Motion was first observed by Nansen on his Arctic expedition during the 1890s. He observed that the ice drift appeared to occur at an angle to the prevailing wind direction. This phenomenon was investigated by Ekman, who formalized it as the Ekman Motion theory. Ekman motion occurs when ocean surface waters are influenced by shear stress from wind. We are interested in this because it describes how shear stress transfers from the top of the ocean surface into the ocean. Ekman motion results from the coaction of wind stress and Coriolis force. First, let's talk about shear stress. On the surface of the ocean, the wind gives rise to a shearing force parallel to the surface. The surface stress at the surface equals the wind stress. The water column starts to move due to the stress. As it goes deeper, both the shear stress and velocity of water decreases. Ekman layer is a boundary layer below which the wind stress no longer influences the ocean. If the ocean is divided vertically into thin layers, the shear stress on each layer is proportional to coefficient of viscosity as well as gradient of velocity. The horizontal force per unit mass due to this shear stress gradient is proportional to the coefficient of kinematic viscosity. And now let's talk about another important force in the ocean called Coriolis force. It's an inertial force that causes deflection of objects that are in motion with reference to the rotating Earth. Deflection is to the right in the northern hemisphere, while to the left in the southern hemisphere. Due to the Coriolis force, surface currents flow at a 45-degree angle to the wind. The velocity spirals with the coaction of shear stress and the Coriolis acceleration, and they are balanced at the Ekman depth, dE, which is the bottom of Ekman layer. The Ekman depth is determined by eddy viscosity and Coriolis parameter. It should be noted that we use eddy viscosity here instead of molecular viscosity, and the turbulent ocean water rather than a laminated one is what we assume. The average direction and volume transport in Ekman layer are a function of shear stress, the Coriolis parameter, and density. It shows that the net transport of water is at right angles to the direction of the wind, clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. At Ekman depth, the vertical velocity of water is determined by the curl of wind stress. The equation here links the vertical velocity to the average velocity field in the horizontal. In the case of a cyclonic circulation in the northern hemisphere, the wind rotates in the anti-clockwise direction with a positive curl wind stress, and water in the ocean will be upwelling. In the case of an anticyclonic circulation, water in the ocean will be downwelling. In a density stratified ocean, Ekman pumping leads to an accumulation or depletion of surface water. The piling up of water in some regions will give rise to pressure gradients that drive geostrophic flow. The Ekman transport can explain the upwelling at the eastern basin margins in equatorial regions as well. In the north, the trade winds moving southwestwards will give an Ekman transport to the northwest, while in the south, the trade winds moving northwestwards will driving an Ekman transport to the southwest. This leads to the divergence of surface water at the equator and upwelling of water from depth. Finally, we come to three conclusions. Ekman spiral results from the balance between shear stress and the Coriolis acceleration. Ekman transport occurs at right angle to the direction of the wind. Ekman pumping gives rise to pressure gradients that drives geostrophic flow. Here are the references for this presentation. Thank you very much for listening.